So, have you ever opened up your company's monthly cloud invoice, scrolled down to the AI usage section, and literally felt your jaw hit the floor, right? If you're building with large language models right now, you are probably nodding your head. Look, we're seeing incredible advancements in what AI can do, obviously, but behind the scenes, there's this widespread, almost silent shock happening in engineering and finance departments everywhere. It's these unexpected, massive AI costs that behave exactly like a leaky pipe.
Actually, Paul Ranjan captures this perfectly in our source text today. He says, most teams discover their AI bill the way you discover a leak, after the water damage. Man, that hits the nail on the head. You think you've got a handle on your prototyping costs, you finally push to production, and then bam. Suddenly the numbers don't just scale linearly, they absolutely explode. And they explode because the fundamental unit of economics in this new era behaves completely differently than traditional cloud computing. You can't just reserve a server and switch it off at night anymore. The whole shebang has changed.
So today we're diving deep into the source text, token economics, mastering the cost, architecture, and governance of AI in the agentic era. And honestly, understanding how this works is absolutely crucial. It is the difference between a wildly successful AI deployment and a completely catastrophic budget blowout. So in this explainer, we're going to translate these dense technical concepts into simple, real-world analogies that actually make sense.
Here's our roadmap. First, we'll look at the AI taximeter. Second, reading versus handwriting. Third, the whiteboard and the check. Fourth, the 3 regimes of cost. And finally, number 5, we'll wrap up with the optimization playbook. Let's get right into it.
Okay, section 1, the AI taximeter, or the atomic unit. So the entire AI industry meters its usage in something called a token, right? Simply put, a token is just the smallest unit of text an AI model reads or writes. As a general rule of thumb, 1 token is roughly 3/4 of an English word. But honestly, the best way to think about this is like riding a taxi in a foreign city. You don't pay a flat rate for the overall trip. Nope, you pay per tick of the meter. And this taximeter ticks in a unit you didn't even choose. Tokens, not words. And it just keeps ticking the entire time the driver is figuring out the route. Now, here's where it gets really interesting. Think about how that taximeter changes depending on the neighborhood you drive through. Because tokenizers were trained mostly on English text, they are highly optimized for it. Common English words get neatly compressed into single tokens. But what happens when you input the exact same meaning, literally the exact same prompt, but you translate it into Filipino or Hindi?
While the meter ticks significantly faster, we're talking 2 to 4 times faster. Non-English scripts can consume 2 to 4 times more tokens for the exact same underlying meaning. So if you're building applications for a global audience, this is a huge structural cost penalty, and a latency penalty too. Built into your unit economics from day one, it's this massive multiplier that hides completely out of sight if you only ever run your tests in English. Moving on to section 2, reading versus handwriting. This is all about inference physics. So every single AI inference call has 2 distinct phases. When you send a prompt, the model reads it in a phase called prefill. During prefill, the model processes all the tokens at once, in parallel, across the GPU. It's heavy on compute, sure, but it is very fast. But when the model starts generating an answer, it enters the decode phase. And decode is sequential. The model has to write 1 token at a time, and for every new token, it actually has to reattend to everything it's written so far. It's heavily bottlenecked by memory bandwidth, which makes it incredibly slow.
To really cement this, the author gives us an absolutely incredible analogy. A model reading your prompt is like a speed reader taking a photograph of a page. It gets the whole thing in 1 quick glance. But a model writing an answer, that's like calligraphy. 1 careful stroke at a time, constantly checking the previous strokes to make sure they align. Photography is cheap, calligraphy is expensive. And this single fact of physics is exactly why AI providers charge 4 to 6 times more for output tokens than input tokens. Makes sense when you think about it that way, right?
All right, section 3, the whiteboard and the check, or where the money actually goes. Okay, so the biggest trap in AI economics is misunderstanding the context window. It is so tempting to think of a 1 million token context window like free RAM on a laptop, but it is absolutely not. Imagine you hire a consultant who can only think about what's written on a whiteboard right in front of them, but the venue charges you to rewrite the entire board from scratch every single time the consultant opens their mouth. That is literally how a context window works. In a chat app, every time you add a new 500 token message, the system resends and rebuilds the entire history of the conversation. So that input cost grows quadratically, quietly compounding into a massive bill right behind the scenes.
And when that bill finally arrives,
It looks a lot like a big restaurant check. You remember ordering the steak, right? That's the direct model inference we just talked about. But when you break down the costs, the steak is just one slice. The rest of your bill is quietly filled up with all these other infrastructure costs: embeddings, vector storage, orchestration compute, observability, and evaluation runs. Inference definitely dominates because it scales directly with traffic. But these other buckets, that's where enterprise budget forecasts typically go completely off the rails. Which brings us to Section 4, 3 regimes of cost: chat, RAG, and agents. So we can break this down into 3 distinct workload shapes. A standard chatbot basically just sips tokens, one prompt in, one response out. A RAG application, retrieval augmented generation, that drinks tokens because every single query stuffs all these retrieved documents and data chunks into the context window. But an agent, oh man, an agent completely runs the tap. An agent runs in a loop. It plans, calls a tool, reads the result, thinks, and repeats. And every single iteration forces it to reread that massive growing transcript we just talked about. A 10-step agent task can easily burn through 100,000 tokens in the blink of an eye. And it gets wilder. If you're using a coding agent, you aren't just paying one bill. You are stacking 4 massive token syncs simultaneously. Think about it. Coding agents require massive context like entire code repositories. Then they run long loops, sometimes dozens of calls per session. On top of that, they generate highly verbose tool outputs like giant error logs and diffs. And lastly, they typically have complex reasoning turned on by default. Put all that together, and a single prototyping session can cost you $7 before anyone even glances at a dashboard. If you accidentally scale that to 400 developers without realizing it, well, you've just discovered that leaky pipe the hard way. Okay, let's fix it. Section 5, the optimization playbook, taking control. This all comes down to routing. I want you to think of model routing like emergency room triage. You don't send the hospital's chief of surgery to put a Band-Aid on a scraped knee, right? Yet so many teams just blindly send every single AI request to the absolute most expensive frontier model available. Don't do that. The playbook here is called the cascade. You attempt the task on a fast, cheap, small model first. You validate it with a quality gate, like basic schema checks, and you only escalate to the expensive frontier model if the cheap one fails. The author actually notes that building this triage portfolio routinely saves 40 to 70% on costs, and that's before you even apply any other tricks. It's a real game changer. Another massive lever you have is prompt caching. Think of caching as that local barista who knows you. If you walk in and just say the usual, it's instant, it's cheap, and it's correct. Providers will actually give you up to a 90% discount on tokens if you ask for them in the exact same order. But, and this is a really big but, if you change even one single character at the very beginning of their prompt, like say inserting a random session ID or a timestamp, well, the barista has to start completely from scratch and you pay full price. So keeping your system prompts perfectly stable is an absolutely crucial first-class metric for cost savings. Ultimately, as you start to master these technical levers, you have to climb the maturity ladder. Look, level 1 is managing the raw cost per token. But frankly, your CFO does not care about tokens. They care about business value. You have to translate those engineering metrics into product metrics. You climb from cost per request up to cost per workflow, and finally, to level 4, cost per intelligent outcome. When you walk into an executive meeting, you don't say, hey, we saved 1 million tokens. No way. You say, our AI now resolves customer tickets for 50 cents each, compared to $10 for human handling. That's what they want to hear. Which leaves us with this final, vital question that you really need to ask yourself and your team. Are you managing the cost of your tokens, or are you managing the cost of your outcomes? The meter never sleeps, but with the right architectural triage, smart prompt caching, and a deep understanding of those taximeter physics we went over, you can transform AI from a leaky financial pipe into a highly profitable engine for your business. So thanks for joining me on this explainer, and honestly, I highly recommend diving deeper into the source text to truly master these concepts for yourself.